to the session on Gusseted base. Now let us try to understand where exactly these column bases are being provided. You've got two types of column bases are there. Based on the load acting on the structure, if the load is less than around 1000 kilonewton, we can go with the slab base. When they come across with the heavy loads more than 1000 kilonewton to 2500 or 300 axial loads, the working loads, you can go with the Gusseted base system of providing the base. Now this type of structures will be provided. I am talking structures means it is with respect to the base slab. The column or the stanchion can be either a single I section or a built up section like this as you are observing it. On either side we have placed the cover plate. It can be a built up section like this, or it can be a built up section with two I sections joined together either by lacing system or batten system, or any other type of system that could be adopted for making it a built up section. Now in this case you are going to study about how to design this base slab, how to design the number of bolts. This is the design bolts that we have to take care. And this plate, what you are finding here in a yellow color, is the gusset plate. Normally in all our designs we are going to take it equal to 16 mm. The angle what you are observing here with a green color is the gusset angle. Nominally we take this as 150 by 115 by 15 mm. It is also not a rule, but only to accommodate the minimum number of bolts here of 4, we are going to use that 150 mm length leg. This will be provided throughout the length of the base plate. This is the blade plate what you are observing. We have to design this width of the base plate, the length of the base plate, thickness of the base plate in this session. So let us learn about how to design those things. And also we are going to design the concrete block, what you are observing here, the width, the length and the depth of the section. This will be designed based on the net upward pressure or SPC of the soil. So normally you will be providing this will be anchored to the concrete plate. The base plate will be anchored to the concrete block by J bolts that we call it as an anchor bolt. Even this has to be designed for tension, but in this session I am not going to teach you how to design the design of anchor bolts. Now let us have a close look up. Whatever the stanchion you have got at the ends, this ends has to be always cut with machine. If you cut it with the machine, the load will be very easily, clearly it will be transferring its load onto the slab, from the slab onto the concrete bed, from the concrete bed onto the earth. So therefore this cutting has to be done with machine. If you do it with machine, the force that will be acting on the one side of the flange connection will be taken equal to 25% of the axial load. If the machine is not cut with machine, it is by hand cutting and saw cutting, then we are going to take 50% of the load for designing this fasteners. This has to be kept in mind and is all as per the code specifications. Okay, let us now have a look on the 3D model of this Gusseted base and try to understand how exactly the connections will be made one by one, and after that we will take up the session on the design of Gusseted base. Now let us go into the AutoCAD session. As I said earlier, let us try to understand this Gusseted base system from AutoCAD. Now we have generated here a 3D model, what you are observing here. A 3D model has been generated. You can see clearly the base plates. These are the gusset base, gusset angles, anchor bolts. The web angle, which is provided nominally, only to keep this position along this direction. It will not take up any load. The complete load will be taken up by these bolts. These are the design bolts. This, as I said, these are the nominal bolts. This gusset angle will run throughout the length of the slab base. This is the width of the slab base. This is the length of the slab base. This length shall not be less than the width of the car plate. If I show you the top view of this one, this is a typical ice section. The total you can see anchor bolts can be provided corners also, no problem. Here these are the ankle bolts, the I section. Car plates, web angle with nominal bolts, the size of the base lamp you can observe here. Let me make you understand by showing this one by one. It's not coming over here, no problem. I'll just close down all the components of the gusseted base one by one. Yes, I am seeing nothing you are seeing here. Now let me try to make you understand how a construction could be done. The very first one I'm going to show you is the concrete block. Over this concrete block, we are going to place the slab base. You can observe the slab base here. I'll show the column section. Now a single column section will be made as a built up section by providing the car plates on either side. Of thickness 20 mm according to the problem that what we are going to take later. On either side of this, we are going to provide the gusset plate nominally of 16 mm thickness. This is the front elevation. Side view. If you want, I can show you the top view also like this. So on either side of this, you're going to provide the gusset angle which will run throughout the length. You can see the gusset angle, a web angle nominal provided. I'll show you the connection details now, the complete detail. The design bolt. So right now whatever the number I'm reading, that is the number design bolt. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 8 is 16 number is the design bolt according to this what I'm showing. And same number of 16 bolts has to be provided in this space. It is not possible for me to accommodate, I have not shown here, but when you show it, you show accommodate that all 16 along this length. These are the anchor bolts. Now if you just hide this concrete block, you can clearly see the anchor bolts. It can be of this shape or it can be of J bolts. This is a concrete. I'll just open it out. Now let us have a view in a rendered manner with a 2D wireframe. This is how it looks. If I hide this, yes, I can make it into black color. You can see it in single color. The front elevation. This is the front elevation. I can have the side view. Depth of the gusset plate you can observe, the length of the gusset plate, the design bolts, the concrete block, the lengthwise and the depth of the section. The last part of this one will be the top view. Eye section, cover plates, the gusset, gusset thickness of the gusset plates, then the angle, the anchor bolts. This is the final view of the gusseted slab base. Now we'll study about the problem design of the gusset base. Now in this part, let us study how to design a gusseted base. Let us take a problem where it is a built up section, column section of grade IS HV 300 at 63 kg per meter with two car plates, one on each side of the flanges. The column carries an axial load of 2500 kilonewton. So we have to design the gusseted base for this column. A concrete pedestal has to be designed. The grade of concrete is M20 and the SBSC of the soil is given as 200 kilonewton per meter square. Now let us see that how to design this gusseted base step by step. It's very simple. Just have a look on the isometric view of the column section, a built up column section. Let us take this itself as ISHB 300, and these are the two cover plates. The depth of the section is 300 mm and the flange width is 250 mm. All this has been extracted from the steel table or from the IS code. Now this has been covered with the cover plate of 400 mm. This is the 400 mm width and 20 mm thickness. The axial load is given as 2500 kilonewton. Since we are designing it by limit state method, as per the code specification, we are multiplying this with a partial safety factor of 1.5. Therefore, the factor load will become 3750 kilonewton, which will be acting axially. In this problem, we have not taken any moment into consideration. This slab base is completely designed for the axial vertical load. Moment is not considered here. Now we can observe the gusset plate here. This is the gusset plate as it was said earlier, and also we have shown you in the AutoCAD. You can see the gusset angle 150 by 115 by 15. This leg which is connected to the gusset plate is of 150 mm depth, and this width is 115 mm, or you can take equal size. There's absolutely no problem. Just we have taken this as an example. The thickness of the angle is 15 mm, and it has been the anchor bolts. Minimum of 4 numbers have been provided here. 1, 2, 3, 4 the other side, and you can see the slab base. This is what we have to design for this load. And you can see the web angle connected on either side, as you observed that in the AutoCAD. And we have to design the concrete block for the SBC of 200 kilonewton per meter square. Now let us see that, how to go about. And what you observe here, this is the design bolt. What you are seeing within this circle is the design bolt. This is the number. So a gusset plate will run up to this depth, means covering all the design bolts on one side. The same number of bolts will be provided on the other side. So in this session, I am going to design for one side of the column, that one side of the flange. Now you are going to consider the area of the base plate. This area of the base plate will be calculated by the formula factored load divided by bearing strength of the concrete. Now this concrete will have the bearing strength that has to be taken as per the code specifications. The grade of concrete is 20, M20 grade. It will be taken according to the page code IS 456 2000, which is given in page number 65 and 66 of the code in clause 34.4. It states that the permissible limit of the bearing strength of the concrete or the bearing stress is equal to 0.45 of FCK. FCK is the characteristic cube strength of the concrete. So all these things you have studied in your RSSC in the earlier semester. But in IS 800 2007, as per the clause 7.4.1, which is given in page number 46 of the code, kindly refer the code, the page numbers, whatever I have mentioned here. Referring to this, in IS 455, the permissible limit has been given as 0.6 times of FCK. So in my problem here, I will be taking this bearing strength of the concrete as 0.45 of FCK. So M20 grain concrete, for that we will be having 20 Newton per millimeter square. So it comes to 9 Newton per millimeter square is the bearing strength, the bearing stress. So area of the base plate will be equal to 3750 is the factored load divided by bearing strength. You will get around 16.61 into 10 to the power of 3 millimeter square is the area of the base plate. I will design the base plate, the width of the base plate according to what all the components we are given here. You got the angles here called as gusset angles. You got the thickness of the gusset plate. We got the thicknesses of the core plate as well as the depth of the stanchion. Based on this, we are going to provide the width of the base plate. The length will be provided not less than either the width of the flange of the stanchion or the width of the core plate, whichever is greater. This length shall not be less than the width of this. So keeping in that view, we are going to design the width and length of the base plate. Now have a look here. Width of the base plate I want to design. I call this as the front elevation. So this is the column we are going to place, and it is called as depth of the stanchion column, plus you are going to put the core plates on either side, which has got a thickness of 20 mm on either side. That is 2 times the thickness of the core plate. Then you got the thicknesses of the gusset plate. I have assumed here a nominal thickness of 16 mm. Then we provide the angles here. The gusset angle, where I said earlier the depth of this section is taken as 150 mm. The width of this connected to the base slab is taken as 115 mm. Thickness of this is 15 mm. This is 115, 150. So keeping in this view, we are going to find out the width. I can provide exactly equal to this depth or much more than that can be provided. Now let us see that how to calculate. This is 300 plus 2 times the thicknesses of the core plate plus 2 times the thicknesses of the gusset plate plus 2 times the widths of the gusset angle. This has worked out to be 602 mm. So now I have taken this to a round number of 650 mm. This is the width. So once we find out the width, the length of the base plate can be calculated. We know the total area is equal to width of the base plate into length of the base plate. Length, it will run perpendicular as you saw it in the previous case. Let us find out that. So length of the base plate is equal to area divided by width of the base plate, 641.02 mm. And as I said earlier, the width of this shall not be less than the width of the core plate or width of the flange plate, flange of the column, which is 250 mm, and width of the core plate is 400 mm. So this value is not less than that. Therefore, I am going to adopt the 641 and I will round it to the next number, say 650 mm. Now the size of the column is fixed, 650 mm by 650 mm. Next is we have to calculate the thickness of the slab base. Now we have got here thickness of the slab base. It will be calculated based on the net upward pressure. We have to calculate first the net upward pressure here. What is upward pressure? That is given by load by area of the base plate provided. Total load was this one, 3750 kilonewton, converted into newtons. The size of the base plate breadth into length is 650 by 650. We get 8.8 Newton per millimeter square, and this value shall always be less than the bearing strength of the concrete. Bearing strength of the concrete we calculated earlier by using the formula 0.45 times of FCK. That was equal to 0.45 into M20 grade concrete. 20 we have multiplied FCK value, we got 99. Therefore this value is less and therefore it is safe. I'll convert this Newton per mm square in terms of Newton per meter, per millimeter. So that means this one along whatever I am going to calculate the lengthwise of 450 mm will be taken equal to 1 mm. Therefore net upward pressure per mm length will be equal to 8.8 mm divided by Newton per mm. Per mm, breadth is multiplied by 1 mm. Therefore we get it as 8.88 Newton per mm. We are converting from mm square to per meter width. Using this net upward pressure, we are going to design the thickness of the slab. In the case of a gusseted base, we are going to calculate the thickness by two methods. Taking the maximum of that, we are going to provide the thickness of the slab base. Now you can observe the front elevation of the system. This is the column, two cover plates on either side. This is the two gusset plates of 60 mm thickness, gusset angle. Now the very first case, consider a critical section. Consider a critical section about the face of the gusset angle. You can either take the critical section XX about the face of the gusset angle, or at a distance a root radius of this angle. It will be given in the steel table. The root radius of this will be given. Beyond this also you can take and calculate. But in my session, I am going to take the critical section about the face of the gusset angle. Either way can do it, but now I am considering this. So when I consider, I will calculate the cantilever distance of this one. The bending moment will be there. Now this acts as a cantilever, this portion. And we know the formula how to calculate the bending moment about the critical section XX. So let me first calculate the cantilever projection. It's very simple. You know the width of the base plate, it is equal to 650 mm minus the depth of the section 300 minus the thicknesses of the cover plates minus the thickness of the gusset angle, and divide this by 2 on either side. You will get the value of cantilever projection equal to 124 mm. And we know the bending moment formula. Its mxx about the critical section will be equal to W into x, acting at the center of this length, into x by 2. Therefore, it is Wx square by 2. Substitute the values of W net upward pressure, the cantilever width or length, whatever you call, get the bending moment. Once you get the bending moment, it is easy to calculate the thickness of the formula which has been derived from the bending stress equation. The T1 thickness, I have designated as T1 and T2 like that, and afterwards we will arrive at T. So it's given by root of 6 mxx, which are all these things you have studied in your earlier semesters in strength of materials. So there is no need to tell you about all these things, how we got all these values. Remember this, T1 is equal to root of 6 mxx by FBS into B. B is per mm width, I said. So we are going to take B equal to 1 mm. FBS is nothing but the bending strength. Bending strength, it is got by dividing the ultimate stress by gamma m naught. Gamma m naught you can obtain it from the steel table. We have got it as 1.1. Therefore, the bending strength of the plate is 222.27 Newton per millimeter square. Substitute, get me the value of T1. It works out to be 42.48 mm. So after calculating this thickness, if you observe here, when I took the bending moment here, it was the thickness of the base plate plus the thickness of the gusset angle was there. The both were contributing its strength to the bending moment value. Therefore, I want to eliminate this thickness of gusset angle, get only the thickness of the base plate. Therefore, thickness of the base plate is equal to total thickness whatever you got with respect to the bending moment value minus the thickness of the gusset angle. So you minus it by 15, the thickness required based on this bending moment value is 27.48 mm. Now let us take another section about the web of the column section like this. Consider another critical section mx1x1 about the center of the web. So I am going to divide this like this, make it a simply supported slab and cantilever slab. I'm going to divide like this. So here the load transformation, we are assuming that the load will be transferred at this end. Therefore, we'll calculate the value of A. A will be equal to cantilever width, what we have calculated earlier, plus the thickness of the gusset angle will get me the value of A. The total width of the base plate is B. So if I take this as A and this one also as A, the intermediate width will be equal to B minus 2 times of A. Now let me draw the diagram, loading diagram like this, a simplified form, and also draw the bending moment diagram for this. So if I just close these two portions, it will be just like a simply supported beam. We know the formula to calculate the maximum bending moment value. It was like WL square by 8. So W is the net upward pressure. L square is nothing but B minus 2A. So this portion from here to here, the bending moment is W into B minus 2A whole square by 8, just like WL square by 8 for a simply supported beam. If I take only this part, and if I take this part, it is like a cantilever. For cantilever, we know that is WA square by 2 for cantilever portion. So that is WA square by 2 here, WA square. This we have taken as negative, this one I have taken as positive. From here to here positive bending moment, this is negative. What is the net effect? Net is only from here to here. Therefore, that is W into B minus 2A whole square by 8 minus this value will get me the net effect of the bending moment at the center. Wherever you consider the critical section, there the net bending moment value is equal to W into B minus 2A whole square by 8 minus 2A square by 2. So you have to remember this. It's very simple. Simply supported portion and cantilever portion. Just we are subtracting it. So let us see that how to get the bending moment. I've used the formula here. The same formula, substituted all the values. I got the maximum bending moment. I call it as YY because I should have made it as X1 X1. Okay, no problem. It's a very minute mistake. You can change it. No problem with that. So Mx1 X1 can be read as 67,210 Newton mm. So for this, we'll calculate once again the thickness. The same formula holds good. I have designated that as T2. So T2 is 6 times of Mx1 X1 divided by FBS into B. B is per mm width. This 1 mm width we are going to calculate per mm width. We got 42.12 mm. So this, whatever the thickness we have got, it will be running in two mutually perpendicular directions. Whatever the moment I calculate at the center, the moment will be distributed in two mutually perpendicular directions with respect to the plan. If you see from top, it will be distributed in two directions. Therefore, whatever the thickness you have calculated has to be made into half divided by 2. So got 21.06 mm. Now we'll come to a conclusion that the thickness of the base, gusseted base, will be taken as maximum of the two values whatever you have calculated earlier with respect to the bending moment taken about critical section and critical bending moment taken about the centroidal section. The maximum of that will be taken. It works out to be 27.48 mm and I have made it 30 mm. Now we have fixed the size of the base plate. The gusseted base plate, instead of calling every time, I can call it as gusseted base. It is of the size 650 mm by 650 mm by 30 mm. This is the size of the gusseted base. Next, we'll see that how to connect this one. The gusseted number of bolts has to be calculated. Let us study one by one how to get the bolt in. We have to calculate first the bolt value for this one, then after get the number of bolts. Now I am assuming here the ends of the column is machine cut. As it said earlier, if it is cut by machine, grinded, we are going to take 50% of the axial load for the fasteners. In that, we are designing on one side of the flange. Therefore, 50% of that 50 will get me 25% of the total column load. That is how we are going to take. If this is not machine cut, ordinary cut, we are going to take complete 100% load, that is 3750 kN into consideration. Divide that on either side, that is 50%. So therefore, when it is hand cut, we are going to take 50% of the axial load for designing the design bolts. I call this as the design bolts. All these bolts are nominal. What we have provided is a nominal one. Simply we have provided there to keep this in position. It has got nothing to do. So this is important for us. Okay. So I have taken here 25% of the axial load of 3750. I got 937. This is important for calculating the number of bolts. First, let us calculate the bolt value. For that, we need to assume the diameter of the bolt and the grade of bolts. In this case, we were going with assuming 20 mm dia bolt and 4.6 property class bolt. Okay, and all these things you already studied in your bolted connections. I'm just repeating that, and it's very easy to understand. You're going to take the diameter of the bolt as given in the code in table 19. For 16 to 20 mm, you are going to take 2 mm extra standard clearance. So therefore, the diameter of the bolt becomes 20 plus 2 equal to 22 mm. Now we have to calculate the strength of the bolt in single shear and strength of the bolt in bearing, and it will be calculated as per the clauses that given in 10.3.3 in page number 75 of IS 800-2007 code. So you know the formula very well. Already you are used to this. You have done a number of problems. Once again, we'll study about that in this problem also. So you have to calculate the strength of the bolt as given in the code Fu by root 3 Nn into ANB plus Ns into ASB by gamma MB. We know Nn means it is the number of shear if the thread is interfering or shank is interfering. In this case, I am assuming that threads are interfering the shear plane. Therefore, Nn exists, Ns will not be, it doesn't exist. Therefore, I can equate it to 0 and this term eliminates. So let us calculate N1. Nn is equal to 1. And gamma MB as given in the code, it is 1.25. In table 5 it has been given, page 30. And A and B, area of the threaded portion is taken as 0.78 times the original area of the bolt, pi d square by 4. So get this much, get the value of VDSP. It works out to be 45.27 kilonewton. So we have done many number of problems in bolted connections. You are used to that, and very fast. You can do it very fast, right? Okay, we'll go with the calculation of strength of the bolt in bearing, which is given in clause 10.3.4 and the page same page number. It's given as 2.5 times KB into D into T star. T star is the minimum thickness. In this case, the T star we are going to take is the thickness of the gusset angle. I'll take it equal to, I'll take this equal to 15 mm. Fu is the ultimate stress of the bolt, and it is taken for the 4.6 grade bolt, it is taken as 400 Newton per millimeter square. Gamma MB from the code once again 1.25. KB, let us calculate it. It is the least of the following. Number 1, E divided by 3 D naught. D naught we know it. E is nothing but the edge distance. It's taken as per the code 1.5 times the D naught. It depends on whether we're going with a machine drilling or hand drilling. Machine drilling we go with 1.5. If you're going with hand drilling, take this as 1.7 times D naught, and it has worked out to be 33 mm, and we have taken it equal to 40 mm. We get the value of E by 3 naught equal to 0.61. The second condition is P by 3D naught minus 0.25. Pitch, minimum pitch I've taken here. The minimum pitch as per the code is taken as 2.5 times the diameter of the bolt. It has worked out to be 50 mm. I can take 50 mm or say 60, no problem. I've taken the minimum of 50 here. got the value equal to 0.51 as per the second condition. The third condition says FUB by FU. Now here FUB and this FUP, as I said earlier in my other session, we have to understand in a different way. This FUB is the ultimate stress of the bolt. For 4.6 it is 400 Newton per millimeter square. This is the ultimate stress of the plate. It is 410 Newton per millimeter square. We get 0.98. The last one is 1. The minimum of this has to be taken. The minimum of this is 0.51, therefore KB is equal to 0.51. Thickness 15 mm. Let us substitute in the formula. We get the VDSP value, VDPB value as 122.4 kilonewton. Then what is bolt value? Bolt value is the least of the strength of one bolt in shear and strength of one bolt in bearing. Whichever gives the lesser value, that will be taken. For shear we have got 45.27, and for bearing we have got 122.4 kilonewton. Therefore, I'll take 45.27 kilonewton. That is a bolt value. Then we'll calculate the number of bolts. So number of bolts is nothing but force acting on one side of the section. As I said earlier, it is 25% of the factored load, that is 937.5 divided by bolt value, we get 20.7. I'll make it an even number, take that equal to say 22 numbers. I have to accommodate all the 22 numbers in this vertical row. Here 11, this side 11, and in this case the maximum number of bolts that can be provided is only 4. Now let us study about the concrete block, how to design the width of this, the length and the depth of this section. It all depends upon the SPC of the soil. Axial load has been given as 2500 kilonewton. We are going to assume the self weight of this concrete block approximately 10 to 15% of the column load. It is approximation. Based on the density, we can calculate the exact weight of this. Now we are assuming say 10% of this axial load. It works out with 250. The total load is 2750 kilonewton. I am not taking here factored load because SPC I am going to use it directly there. That is not factored or anything. Therefore, I am going with axial load of 2500 kilonewton. Now we have to fix up the depth and other things, the area size of this one. We know the area of the block is given by total load divided by SPC of the soil. Total load is 2750 by 200, we get 13,500. Whatever may be the shape of the base plate, it can be either a square base plate or a rectangular. Let us design a square concrete block. Now here in our case, the base plate is a square base plate. It is 650 mm by 650 mm, that is 0.65 meter. Whereas even if you get a rectangular base plate, you design a square concrete block. So we are going to take the root of this. I'll get the side of the block. It is 3.71 meter. So 3.75 meters are taken. Now thickness of the concrete block. This depends upon the load dispersion. Normally the load that will be transferred from the column, it will be transferred onto the base plate, from the base plate onto the concrete block, from concrete block onto the earth. So it will be having a dispersion angle of 45 degree normally. All load dispersions will be of 45 degree angle. So this is how it goes. So depth of the section, since it is 45 degree, the depth of the section will be equal to this projection beyond the point from where the load is being dispersed. Therefore, we have to calculate the projection of this. It's very simple. 3.75 minus 0.65 divided by 2 will get me the projection. That will be the depth of the concrete block. You can observe here, depth of the concrete block is equal to projection beyond the base plate, because it is a 45 degree, this projection will be equal to the depth of this concrete block. To get 1.55 meters, I just made it as 1.6. That is the what we are providing here. This is the final design. 3.75 meter by 3.75 meter by 1.6 meter is the size of the concrete pedestal or block, whatever you call. This ends up the design part. If you are interested, you can also go with the drawing part. The drawings and other things will be definitely explaining in any other session how to draw about that. Right now I am showing you directly the front and side elevation of the gusseted base. This is the depth of this section, the two car plates, the number of bolts have been accommodated here. So here totally you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The same, the other side will be there. You can observe here 11 this side, 11 this side. This is the shape of this from architectural point of view, we have just tapered it. This is the minimum pitch distance, edge distance, and this is the pitch. And here when you come here, we say that the same number, whatever the number of bolts you are given here, the bolts that you have designed should be provided here to keep intact the gusset plate and the gusset angle. And at the bottom you can show the anchor bolts. Now you can provide it nominally with a 20 mm dia bolts. You can anchor it to the concrete block. Now let us observe the plan of this. When you see it from the top, you can see the eye section. On either side the cover plates. The width length of this is 400 mm, thickness is 20 mm, and this is the thickness of the gusset plate of 16 mm thickness. The gusset angle from here to here of 115 mm. The thickness of the gusset angle equal to 15 mm. You can observe from all the four corners, you can see that anchor bolts have been provided. This is the top view of the gusseted base. The next one you can observe, I am just showing to show you just a photograph that has been taken on one of the bridge site where when I had been to Salem. This is the built up section with two eye sections joined together by lacing system. Here the lace, what you are lacing, what you are observing is an angle. Let us speak about all these things in detail, how to design all this built up section using different types of lacing system. That we'll study about. Now we will concentrate on how the slab base has been. This is the slab base, this is the gusseted plate. This type of stiffeners are provided for the welding purpose. This is a welded type gusseted base. Welding will be done inside, welding will be done outside. Welding here inside, welding here it will be done inside. You can observe here. These are the vertical stiffeners, and this is a stiffener for the column. Let us not worry about that right now. This is another view. Hope you understood the design part of the gusseted base. If you like it, kindly comment on this one in the channel and also share this. Thank you very much. Please subscribe for this channel. Thank you once again.